right, we just finished watching a video on how big the mole is, and we saw that Avogadro was inspired to help make some and simplify some calculations in chemistry. He reasoned that if one atom of hydrogen weighed 1 AMU and an atom of oxygen weighed 16 AMU, by weighing 1 gram of hydrogen and 16 grams of oxygen, we would have an equal number of atoms. In fact, if we weighed out a relative atomic mass of any element in grams, we would always have the same number of atoms. He called this number of atoms the mole. Okay. So if we take a look at 1.01 grams of hydrogen, and 12.01 grams of carbon, 16.00 grams of oxygen, and 35.45 grams of chlorine, they would all have the same number of atoms. So the word mole is similar to other words in our language, which stand for a particle count. When you buy donuts, like we saw in our video, we often ask for a dozen donuts. Whether we buy a dozen chocolate donuts or a dozen glazed donuts or a dozen jelly donuts, we always get the same number of donuts. Likewise, 1 mole of oxygen atoms or 1 mole of carbon atoms or 1 mole of hydrogen atoms is always the same number of atoms. Avogadro was not able to determine how many atoms were in a mole, but that didn't matter. All that mattered was that a mole of any kind of atom was the same number of atoms. So moving on to page 47. Today, we were able to do experiments that allow us to count atoms. We now know that 1 mole of atoms equals 6.02 times 10 to the 23rd atoms. That is a really large number, that just like we saw in our video. So 6.02 times 10 to the 23rd atom is 602 with 21 additional zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21. So rather large number, which is why we want to use scientific notation, 6.02 times 10 to the 23rd. All right, so 1 mole of oxygen atoms equals 6.02 times 10 to the 23rd oxygen atoms. We also know that 1 mole of hydrogen equals 6.02 times 10 to the 23rd hydrogen atoms. 1 mole of donuts, 6.02 times 10 to the 23rd donuts. 1 mole of pencils, 6.02 times 10 to the 23rd pencils. So the number of particles is always equal to 6.02 times 10 to the 23rd particles. Just like if I had a dozen pencils, I would have 12 pencils. That same idea. All right, well, molar mass. So we've already learned that the mass of 1 mole of any kind of atom is determined by looking up the element on a list of relative atomic masses and expressing that in grams. So 1 mole of copper is 63.55 grams of copper. So where are we getting that number from? So I should have mentioned to begin this lesson, what we need is pages 46 and 47 in our packet, and we'll move on to page 48. A pencil would be helpful, a highlighter, and then you're going to need a calculator, and then finally our periodic table. Okay, so where does 63.55 grams come from? So 63.55 is the atomic mass on the periodic table expressed in grams. We will always round this number to 2 decimal places, as we see on our periodic table. And our unit will no longer be AMU, it will be grams per mole. So we have a couple of sample problems here that calculate the molar mass of water. And then we have potassium dichromate down here. We are going to move ahead and jump over to page 48 so that we can work through a few problems together. All right, so periodic table handy, calculator handy, and a pencil. All right, so if we take a look at iron, Fe, we want to know the molar mass of iron. So what am I going to do? I'm going to go to my periodic table. I'm going to look at iron and I see 55.85. So iron has a mass of 55.85 grams over 1 mole. So grams per mole. Sodium, for our next one here, just going across to the right. Sodium, element number 11, has a mass, an atomic mass of 22.99. That 22.99 will be expressed in grams per 1 for the molar mass. Okay, so for a single element, you're just going to look at the periodic table, pull that number off, give it a unit of grams per mole instead of AMU. Now, let's take a look at cobalt 3 chloride. So cobalt 3 chloride, we're looking at 2 different elements. So I'm going to take CO and my chlorine, Cl, and make a list. So in my formula, I have 1 cobalt. I'm going to multiply by the molar mass that I find for cobalt, which is 58.93. So I'm going to take 58.93. I'm going to multiply that by 1, and I get 58.93 grams per mole. All right, for chlorine, I have a subscript of 3 here. So I am going to take 3 times the mass of chlorine, which is 35.45. I'm going to take 35.45. Okay, I'm going to multiply that by 3. So I'm going to put this in my trusty calculator. 3 times 35.45 equals 106.35 grams per mole. Okay, and to get the molar mass of the entire compound, I am going to add these together. So my 106.35 plus 58.93, and I get a total mass of 165.28 grams per mole. Okay, question always is, do I need to write my units? And the answer is absolutely yes. Okay, units are incredibly important. We're going to be using them quite a bit as we move forward. If you're missing the units, there's a bigger chance that you're going to make a unintended mistake because you don't know what your number is representing. All right, so we're going to jump down to another example with parentheses so that we can practice counting those atoms. All right, so I have magnesium hydroxide here. So I'm going to list my elements. So I have magnesium. Hydroxide is made of oxygen and hydrogen. My formula does not have a 1 behind it or a subscript behind magnesium, so it's assumed to be 1. Oxygen is in parentheses. There's a 2 on the outside, so there is 2 times 1, so 2 total oxygens. Same thing with hydrogen. Distribute the 2 to the subscript that's behind hydrogen, which is 1. So I get 2 hydrogens as well. So then my magnesium, my molar mass is 24.31. So for a total of 24.31 grams. All right, so we're going to keep going with oxygen. Oxygen, we have 2 in our formula. Oxygen's molar mass is 16.00.